Hello, everyone. Thank you so much for coming. This is my first talk ever, and I'm so excited to share with you my talk about what's the performance overhead in tracing. I'm Gabriela Soria. I'm a former Outreachy intern for CNCF, and I want to spend a few minutes to talk a little bit about Outreachy. Outreachy is an initiative of Software Freedom Conservancy and provides 3 months paid internships for underrepresented people to work in free and open source software. This talk will cover the results of my internship working with OpenTracing and JAX communities. If it wasn't for the opportunity that Outreachy gave me, the encouragement of my mentor to present this talk, and the CNCF Diverse Scholarship, I'll not be here. And I want to say thank you, thank you, thank you. This is the agenda for the topics that I'll be covering today. First, for the people here that are not familiar with some concepts, I'll give you a brief review about microservices, distributed tracing, OpenTracing, and JAX. Then I'll be presenting how the tests were built, showing an example and presenting the results. And then I'll share my opinion about what should be the next steps for this work. So, a brief introduction about microservices. This Martin Fowler's image is probably one of the most famous images about microservices and helps to show the big differences between a monolithic application and one microservice application. Microservices are an architectural style that propose to have independent, loosely coupled services responding to a business responsibility. It means that the responsibilities of our entire application are spread into multiple services. This architecture has so many benefits. We can deploy more frequently. We have freedom to choose the right technology for the problem we are solving. But also, this architecture adds some challenges, as for example, understanding the transaction flow from one request through all our system. And that kind of problem can be solved using distributed tracing. Basically, distributed tracing is a method to profile and monitor our applications. It helps to understand the behavior of our application and the flow of our transaction. But the most important, to detect performance issues. On the other hand, OpenTracing is a project sponsored by CNCF that provides an standardized API to allow to write the traces in a vendor-neutral way. This means that if we decide to instrument our application today, and today we choose one tracer implementation, and in the future we need to change it, we don't have to change anything in our application except the tracer implementation. And JAX. JAX is an open source distributed tracing system sponsored by CNCF, which implements OpenTracing. This image shows a trace detail view. A trace can be thought as direct acyclic graph of spans. Each row here is a span, The span is an unit of work, and it has the operation name, the start time, and the duration. So let's move to talk about the tests we built. These are some considerations that we took before building the test. We use a toolkit created by OpenJDK to build benchmark tests. It is called Java Microbenchmark Harness, or GMH. The results that we got after the execution of the test, we processed with this amazing tool called GMH Visualizer. And the scope of the test that we built is just for OpenTracing Java, and we hope to extend to another language in the future. And we have various benchmark tests, and for all that was possible, we tried to avoid network calls in order to have the deltas the most isolated possible. Here you can see the command for start a new GMH application. This is a standard Maven command, and the important thing here is the archetype group ID, which is referenced to GMH. And with this command, we create a new project with the required libraries and with the required plugins for GMH. And this is how one of our tests looks like. In this case, this is a test for OpenTracing for Spring Cloud. And here we can see that it's a normal Java class with methods, but the methods that we want to benchmark have to be annotated with benchmark. And also, we can put the mode of the benchmark. For example, if we want to measure in the average or the simple time or the throughput. In our case, we decided to separate the modes because the results that we got separate the modes were more easy to represent graphically with GMH Visualizer. And we have one method with known instrumentation and one method for each tracer implementation that we want to test. We want to benchmark. This is another important part of the benchmark test. And sometimes you want to initialize some variables that your benchmark code needs, but you don't want to be part of the code that your benchmark measures. And for example, in this case, we initialize the Spring context, and we assign a variable with the controller that we need to use after in the execution of the test. Also, after the test finish, we close the Spring context. And here we have classes extending the state variable classes that we've seen before. And with these classes, we use Spring profiles to set the property for inject the right tracer implementation for each test that we are trying to build. So after we have the test, we need to generate the project. with this Maven standard command, and we run the benchmark with this simple Java command. And the results of this are JSON files in a subfolder of GMH, in a subfolder of each project, and start with the prefix GMH something. And these files are the input for generate the graphics using GMH visualizer. So this is a list of the tests that we built. We started with a simple Java scenario with the instrumentation written manually. And this scenario only tests an string concatenation, like concatenate hello world and one iteration number. And with this scenario, we don't have either HTTP calls or frameworks involved. This scenario doesn't represent a real use case, but it provides a very good baseline of the theoretical limits of the tool involved. Then we have an Spring Boot project. We did the instrumentation manually too. And in this project, we simulate a billing process, like generate line items, notify the customer, calculate the taxes, etc. Another test is the Spring Boot. And here we use the dependency OpenTracing Spring Cloud started. And we use the pet clinic sample application, officially from Spring. And here, there is no HTTP calls involved. That it means we call in the test to the Spring service directly. Another test is the JDBC. We use in-memory database, H2. And we instrument the application using the library OpenTracing JDBC. This application is an example of course management. And in this example, we call in the test to the directly to the Spring services. And for the last two set of tests, Servlet Filter and JAX-RS, we did network calls. The part of the test execute an HTTP call to perform the test. In the case of Servlet Filter, we use the dependency OpenTracing Web Servlet Filter. And in the case of JAX-RS, we use OpenTracing JAX-RS Discovery. And the tracer in the last two tests is registered in the global tracer using an application listener on the startup of the web application. So let's see the results. For this simple Java scenario, the test execute a simple string concatenation, and the test compare a non-instrumented scenario with instrumentation with different tracers. We can see in the x-axis, we can see we use haystack tracer, Jaeger tracer, mock tracer without instrumentation, and knob tracer. Let's analyze the numbers. The numbers for non-instrumentation and knob tracer are very close and equal in some cases. Mock tracer is not a very good comparison because it's not intended to be used in a production environment and keeps the spans in memory that degrades the performance. So for this and the other scenarios, we will compare the non-instrumentation with Jaeger tracer. We also have tested haystack tracer, but just as a reference point. You can see in a blue line here. I'm not showing the numbers in the slide, but according to the numbers, the sample time increases around 4,400% in this simple scenario. And it's not intended to, it's not easy to see here because the graph is distorted by mock tracer and haystack tracer, but that's the number. And if we see the other metric, the throughput, we can see that the throughput decreases by around 90% in this simple Java scenario. This case does not represent a real use case, but it provides a very good baseline of the theoretical limits of the tools involved. And the big overhead here that we see when using a real tracer is indeed expected and is a sign that the benchmark is sane. So let's move to more real-world scenarios. Here we can see the results for the Spring Boot application containing a billing process. The application is initialized in each test iteration, and using profiles, the right tracer is injected. The different tests measure the process of issuing an invoice in a non-instrumented scenario and instrumented with different tracers. The sample time increases around 200% in this Spring Boot scenario. And if we see the throughput decreases around 67%. Let's move to see the results for Spring Cloud. This test used the Pet Clinic sample Spring-based application, and the application is initialized for each test, and using profiles, the right tracer implementation is injected. And the different tests measure the process of finding a pet owner by ID in a non-instrumented scenario and instrumented with different tracers. The sample time increases in around 4% in this scenario, and the throughput decreases around 8% in the Spring Boot scenario. So let's move to JDBC. This test uses a simple boot application containing a basic course management process. The application is initialized in each test iteration, and using profiles, the tracer is injected. And the test measured the process of getting all the list of all the courses in a non-instrumented scenario and instrumented with different tracers. And the sample time here increases in 13%. and the throughput decreases around 8%. So if we move to the test that involves HTTP calls like Servlet Filter, for this particular test, we use a Servlet simple application to process a GET and return an HTML page with information of the request and a random number. And using understow API, the servlet is deployed and the right tracer is injected. And with listeners, we register the tracer in the global tracer. The test consists of making a simple request to get a hello world page in a non-instrumented scenario and instrumented with different tracers. The metrics here show no evidence of overhead, as the deltas of throughput and simple time are not representative. And here we can see the graphic for the throughput for the case of Servlet Filter. And the last scenario is JAX-RS. The test here use JAX-RS with Spring Boot application containing a basic course management process. This application exposes a JAX-RS endpoint called course resource. And the application is initialized for each test iteration, and using profile, the right tracer is injected. The tracer is registered in a global tracer at startup using a listener. And the test consists of a client REST call to get the list of all the courses in a non-instrumented scenario and instrumented with different tracers. And here also, the metrics shows no evidence of overhead, as the deltas of simple time and throughput are not representative. So, in conclusion, the overhead comes from the actual tracer and is closely related to how they work and how they are configured. In simple Java scenarios, the throughput decreases around 90%, and the simple time increases around 4,400%. In this case of the simple Java scenarios, it's not a real use case, and the overhead that we see here is indeed expected, and is a sign that our test is sane. In scenarios that include calls through the framework like Spring Boot, Spring Cloud, or JDBC, on average, the throughput decreases around 12%, and the simple time increases around 14%. I have to mention that these numbers are comparing a non-instrumentation scenario and with instrumented with Jaeger tracer. And in the scenarios with client calls through HTTP, like Servlet Filter or JAX-RS, the metrics show no evidence of overhead, as the deltas of throughput and simple time are not representative. So, the next steps, in my opinion, is test with specific concrete tracers, such JAGRs or other, to understand how much the overhead can be controlled modifying the configuration, as for example, sampling or different protocols or different backend configs. And these tests can be used with the merging of OpenTracing and OpenCensus, to understand if the changes introduced in the process affect the performance. Thank you. Here is the link of the repo and with the results. And if you want to keep in touch, this is my Twitter. Thank you.
Are there any questions?
I was wondering, you said there were no evidence of overhead while you're doing the HTTP calls in the last two test cases. Seems a bit odd to me that there's no overhead in executing additional code. So did you consider that it could be a problem of you did not put enough load on the via the network calls on the system you try to measure, or have you another explanation why there's no overhead?
I'm not sure about the answer of that question, but I think if we consider it the cost of the test proportionally to the cost of the network and I/O, the delta is not representative. Yeah, but that can be an improvement to the test. Yeah.
So I know for tracing, usually the advice is to sample like something like 1 in 1,000 requests for actual tracing. Based on this, since real tracing typically has HTTP requests, it seems like the only reason for sampling would be to reduce the burden on the actual tracer. There's really no risk. I guess, would you say that it would be okay to trace every request since there's no apparent overhead, and that wouldn't hurt your application's performance?
Sorry, I don't understand the question.
Well, I can rephrase. I was kind of wondering. So I've wondered if it's okay to sample every request for tracing, or if that's risky because that could cause too much overhead. Would you say that it's okay from a performance standpoint to trace every request?
Yeah. The approach that we use is sampling all the requests, but maybe was not the best. Actually, that was one of my points in the next steps. It will be important to understand if with sampling we have different deltas and with different numbers. But with this configuration, sampling all the requests, the overhead of the test with non-instrumentation scenarios and instrumented with Jagger were not representative.
I also think that the load on tracer backends might be problematic.
Thank you for your talk. I was wondering about the graphs that you showed. What did you show different runs, or what was the x-axis, and why was there a graph drawn between the data points? What was is the meaning of that?
We didn't have proxies involved in this test. We tried to measure the most isolated possible the overhead. Having one application and instrumented that application and calling to the Spring service directly when was possible, and in scenarios when that wasn't possible, we use HTTP calls for do get requests or something like that. But this is one of the scenarios that probably we have to stand in the future.
Okay, yeah, I understand your test setup, but I was wondering did you consider showing the data in a table with error bars, or what is the significance of having the data points for one setup distributed over the x-axis if they signify different run instances?
I don't know. I don't know the answer for that question. Sorry? Oh, we measured the test multiple times in the graph that we saw. Let me show one of them. Each of these points were one execution, and we compare with different configuration with multiple executions. And the patterns were the same.
I think the question was why you chose this representation instead of just like average and like error bars, min-max, whatnot.
Yeah.
So the idea is there to see the standard deviation as well. So if we have a lot of variation between the runs, then we know we have to look into that. But if they are quite continuous or quite linear, then we know that it's consistent. The results are consistent. Because the problem with performance tests is you don't know if what you get is really what you are testing. But if you have high variance, then you might not be testing the right thing. Yeah, so that's mainly the reason why we have multiple dots there.
Thank you.
Any other questions? If not, thank you again.
Thank you.